In this video, we discuss what fairness practice is in ML and data science, its basic nomenclatures, and some short intro about metrics and bias handling. So let's start. Fairness is a sociological concept incorporated into the ML and data science practice. It discusses providing equal opportunities for all, regardless of gender, race, religious belief, disability, and other sensitive information. This information is termed protected data features or even sometimes demographic features, provided the second one only contains demographic information. In a discussion about fairness, there is a debate about equality versus equity or blind neutrality. Equity is a socio-economic idea based on the contribution of a person or group to the system, which is often measured directly. Fairness practitioners frequently debate this, saying it does not consider many social biases. So, alternatively, they emphasize equality for all. Fairness practitioners propose including socio-economic factors while designing a socio-technical system. After all, technical innovation has a multidimensional impact on socio-economic standards. Better technology results in a better life and human experience. Let's see how a lack of fairness in ML and data science practice can have some socio-economic impact. It is said that a model that adheres to the social bias rather than mitigating it is bound to create more discrimination. For example, a credit defaulter detection model is almost 90% accurate but fails to perform similarly for persons of color. Persons of color occupy a significant portion of the population dataset. As a downstream impact, that model is causing economic discrimination against a section by not recommending loan sanctions for them. AI fairness practitioners say this phenomenon should be seen from a socially empathetic angle rather than high technical accuracy. The previous example discusses only one specific group, depending on the color. Many criteria can be used, such as financial and marital status, gender, ethnicity, age group, geographic location, etc. Discrimination also occurs accordingly, which may impact in turn overall socio-economic growth, the revenue of a company from a region, gender balance, and other factors. Therefore, AI fairness practitioners emphasize mitigating those model biases with some recommended methods. Before that, we need to discuss bias in more detail. We start with social bias, which is present in the system. This bias is introduced when sensitive or demographic information is included in the system or data storage. Sometimes this inclusion is not explicit but instead happens unintentionally. Although their information is not explicitly captured while collecting data, giving preferences to specific privileged groups may cause this bias, affecting the ML model later at inferencing stage. For example, to infer sales of any consumer product, if the buyer's information is collected majorly from a specific income group, some people may miss the discounts the brands give to those who don't belong to that group. Next is the technical or statistical bias. It is the effect of differential accuracy or outcome rates across different regions of the data the model trained on. Let us understand this next. As shown in the picture, a model gives 80% accuracy for feature group A and only 50% for feature group B. Let us understand what these feature groups are. A and B, as shown earlier, can be some values of a categorical feature or combinations of different features. They also can be clusters representing the outcome of a clustering algorithm. Now we see how to compute the metrics of fairness standards. We start with a DIR, which stands for disparate impact ratio. It is the ratio of model outcomes of the protected group to those of others. If the A is the protected group, it is expressed as shown on the screen. Model outcomes can be scores of likelihood or even accuracy. We can even use their model metrics like false positive rate, F1 score, etc. Now the question is, what's the optimal value to target for DIR? The US government department set one practice of keeping it at 0.80. Ideally, it should be 1, but that's a hard target. The goal is to make the model behave homogeneously across all data regions that contain sensitive information. Another similar metric is the mean difference. Here we take the difference in mean outcomes instead of the ratio. This works well for regression problems. Model performance across groups can also be measured using error rates instead of positive outcomes. A fair model is expected to produce the same error rates for sensitive data groups as for non-sensitive ones. After all this, we enter the solutions part. That is how to mitigate bias and introduce fairness into the ML models. One common way of doing so is by hyperparameter tuning and cross-validation. Both are similar because they are unrelated to the model's internals. Any hyperparameter tuning algorithm like Bayesian optimization can do this with the objective function set as any fairness metric discussed earlier. And the same goes for the cross-validation method. The earlier method could be more directionless, leading to the wrong model selection or exceptionally time consuming. As a workaround, AI fairness practitioners suggest 3 methods: pre-processing, in-processing, and post-processing. If you want to know more about Bayesian optimization, the link is given below in the description section. Pre-processing. It is the early prevention of the bias before modeling. If done properly, then it can mitigate a lot of downstream effects. One way of doing this is removing the sensitive and their correlated attributes from the dataset, aka super suppression. Other methods includes resampling and reweighing the dataset. Reweighing is like handling the class imbalance problem by assigning a weight in the loss function for each record. In processing, it is the most complex method. This is where we are supposed to optimize the model. In some cases, data pre-processing may be difficult due to licensing or organizational restrictions, making in-processing very helpful. One way of achieving this is by using a regularized loss function, similar to the regularization done to mitigate overfitting problems. The loss function should include extra terms with first or second order correction terms. Another way of handling in processing is using an extra adversarial model, which will try to outsmart the original model. Ultimately, an optimal fair model is produced with a handshaking mechanism. The adversarial model tries to predict the sensitive attribute from the outcome of the original model, and the iteration continues until it cannot do the same anymore. The overall loss function is adjusted accordingly. Next is post-processing. This method is most straightforward but requires a cautious approach as it involves modifying the model outcome to maintain specific fairness metrics without knowing the model internals. One possible way to do post-processing is to give preferences to the positive outcomes for the sensitive data groups. I will make separate videos on each of these processing methods later. Like any other AI initiative, AI fairness practice is not free from debates. Few AI fairness critics raise two primary sources of debate: slowing down innovation and injustice to merits. AI fairness practitioners often counter these points by saying that this practice makes room for innovation by all, new methods, new models, and so on. It's a matter of political discussion, and at least in this channel, we don't want to go there in detail and decide who is right or wrong. Our only goal is to learn the computational methods behind fairness practice, and that's all. If you like the video, please share, like, comment, and don't forget to subscribe to my channel and page.